Hey, I think it's working. I'm gonna just pretend it's working, and if not, well, oh well. So, welcome back. Thanks for coming. Um, Everybody should have received your homework 3 grade.
Mm-hmm.
Cool. If you need help getting that in, I know it's kind of a quick turnaround to get it in by Friday, but most people only needed like it's usually either reliability or graphs, right? That's usually what's missing, and so we can get. That's a matter of like fighting with R, but we can help. I can help fight, and so can Lou. And if it's not in person, then we can do that over email as well. Certainly okay. I have a little bit of time after class. I know a couple of you want to talk to me then, so that's good. I have until about 2:10, and then I got to walk to the Watson Library to meet for another meeting and then walk back. So, but then I am also available on email, so please do email me. One thing I wanted to ask after reading first of all, I think everybody to a person did really well. You may not have had the top number of points, but that's because again, you can fix that. It's not about you're going to get the full grade. We'll all get there, right? But I think just the concept. If you look at it from a pedagogical standpoint, like what you've learned, how to do things, I was very happy with. That's really cool. I'm excited. I'm actually getting goosebumps. I'm like, you guys are pretty bright. I'd like to ask you, just as your sort of a qualitative reflection here. What is your reflection about the experience? What did you think of the homework, looking at the data? Did you learn anything new about your data? Yeah? Anybody want to suggest anything? I know some of you. See, I know all of your things. I don't want to like share. It's private information, so I'm not sharing it. But I know at least one or more of you had done multiple iterations to try to get a model to fit. Did you find that to be difficult or frustrating?
That was my favorite part. I liked that.
Really? Okay.
I was like, what's it going to do when I click this time?
Okay, cool. Because there are certain times, I swear, like, you could be given months to do this, and it would never work.
Mine didn't end up working. I think I got it like 0.93 or something, but it started
It's still
at
pretty.
0.5.
Yeah.
So.
Yeah, it's still pretty a big improvement. Yeah. I thought another thing that was interesting was that, I don't know where that went now. Here's my window. Oh, I know. Nope, maybe not. Anyway, I thought it was interesting how... stop mirroring, that's why. Oh, never mind. Give me a moment here. I freak out when the technology goes bad, and I'm trying not to yell at it, because I've heard that's really bad form, too. My first inclination with technology is to just curse at it, or then turn it off and turn it back on. And if that doesn't work, then there it goes. I kick it, and then I turn it back on, turn it off, and turn it back on again, right? So it's how I call my tech man. If you call me for tech support, it would be turn it off, turn it back on again. If it's still broken, kick it, turn it off, turn it back on again, right? Anyway, so yeah, I think in my experience in doing this the first time, when I did CFA the first time, or when I really looked at it at a different project, a couple things stood out to me, which was how incredibly difficult it can be to sort of see all the moving parts moving together. Like you make a change here, and something else changes here, and then whatever else. And I think that's part of it. It's really I wanted to give you an experience in unpredictability. So there you go.
So because of the assessment that I used, it set up so that it has 3 dimensions, but you allowed me to do the only one.
That's right. Yeah.
So I just knew that like, okay, this reliability would be different if I include all 3 dimensions.
Yes.
So it's just like practice purpose. But then like I was a little bit weirded out using modification indices because you said voodoo.
Yeah.
But at the end of the PowerPoint, you said, "Oh, just keep in mind that like only to repair your current model."
That's right. Yeah.
So I'm like, okay, so this is the rationale for me to use this.
Yeah, that's fine.
I just needed to repair my current model. But anyway, I'm interested in to include all 3 dimensions.
Well, you've got a really interesting design. Sorry. So you have you showed me this grid where you had a question, and then you had 3 different ratings for the question. Each of those ratings went to a different dimension. But if you think about it, each question is sort of a common stem, and that needs like a methods factor per question. All right. So your design would be really complicated.
Yeah. So
yeah.
it'd be interesting if this process even going to change
Mhm.
when including all three. So
Yeah, I don't know. That's a good question. So modification indices, I call them voodoo mainly because my wife does. But no, I'm just kidding. I think the bigger picture is this. If you think about what you're doing with a sample. So you could take a sample of people, you give them a survey, and you had this idea in mind for what you wanted to measure when you created the survey in the first place. And ultimately, invariably, it didn't work. I think maybe there were one or two of you that got things to work on the first try, but it seemed...
That's really lucky.
Yeah, it was like, yeah. So ultimately, then what happens? Okay, so you look at whatever index you can, whether it's modification indices or normalized residuals or whatever, and you make a modification. So the question is that modification now indicative of something wrong with the trait, right? So now the trait sort of changes, or is it something wrong with the item, or is it something wrong, you know, or is it just that quirk of that sample that's you know? So all those are potential issues for where it could go awry. And I think the problem is that when you only have one sample, because data is expensive. And I always like to say, like, you know, everybody talks about big data these days. If you collect it yourself, everything's big data, right? Right? So because of that, in theory, when you make that modification, you should sort of go and validate that with another sample. Like, okay, so now, you know, my construct has changed. I'm going to go grab another sample and see if it's consistent across these samples. But the reality of it is it's probably not going to be also, right? And that process can go on and on and on. So it's sort of this balance between trying to make modifications so that you get enough model fit to believe the result, but still have the construct in a form that's roughly equivalent to where it is before. But there's always opportunity for people to pick at it because it's not, you know, the actual confirmatory factor analysis invariably ends at the first step by saying, no, it didn't work, right? And so then it becomes somewhere in between exploratory and confirmatory. So it's a tough spot to be in. So yeah, there's a lot of variability across fields, across people even who are prominent in structural equation modeling at CFA would do things differently. So it's tough to sort of see how everything works together. But understanding that as you go forward, it's somewhat nebulous, and there's certain... The few things that are agreed upon is model fit's important, because otherwise the results may not be accurate. And then after that, you know, there's sort of a relatively roughly agreed upon framework for what model fit is. But after that, it seems like it's tough to say where it goes. I was just reading David Kaplan, who's one of my favorite people in the field for a number of reasons. But he has a book on structural equation modeling. He also has a book on Bayesian statistics. And there's a chapter in there, Bayesian statistics book, about CFA. And he was talking about, well, a lot of people call this confirmatory factor analysis, but I don't really like the word confirmatory because ultimately this is the process, right? The confirmatory sort of stops at the first step, right? And invariably, how many of you had the first analysis you didn't fit? Most of you, yeah. That's life, right? So, okay. Yeah, Shada.
One of the things that I realized in this assignment was that I used to think that it was just like you get all the data, you know, from each of your items, and then you plug it in and you kind of mess with it a little bit to see if you can get good model fit, and then that's it.
Mm-hmm.
You never really return back to the items.
Mm-hmm.
And at least for my analyses, that wording of the items really impacted the model. So accounting for those wording differences improved my model fit. I never got good model fit.
Oh yeah, right,
but
yeah.
Even when I did do positive and negative method factors, this didn't work.
Yeah.
Not work, but it wasn't.
No, I totally agree. Yeah.
But it was a little bit better. So understanding how sometimes you do need to go back to the items to understand what's happening was really interesting because I never really thought about it that way.
Right. Sort of the items are sort of they were, you know, written in stone, and you just got data from them, and then you just go and that's good. But I think the other part of that too, if you think about it, thinking forward, if you were to write a survey or a questionnaire and you realize that wording differences might be so big, you know, keep that in mind as you're writing the items, and then examine patterns and try to make it so that, you know, if you have similar wording that it's purposeful, or maybe you can avoid having similar wording or something like that. It's not always possible. I mean, language is messy. Anyway, yeah. So
when
Yeah,
you
yeah.
say that confirmatory factor analysis stop in the first place, this is in the case even if you deleted items.
Right. I mean, so ultimately you're making another modification, right? Because you were going to confirm a model with a set of data, and you disconfirmed it. You said it's not there. Okay. Next. Well, why did you delete the items? Well, I looked at the results, and they told me this is what's happening. That's sort of modifying it based on empirical data, which is what you should do, but that's subject to error in the sample, you know, generalizability of the sample, and all the other parts that would do. But the bigger part is it's no longer confirming, it's guessing and checking now, right? Whereas the first time was I have this survey, I have this data, this is what's going to happen, I'm going to check, and then it didn't work, right? So I think that's where I would say like the true spirit of confirmatory really only happens up until you disconfirm it. And after that, it sort of becomes somewhat exploratory, right? So yeah, I think that, and I do think the wording is sort of a misnomer. Exploratory versus confirmatory. It's sort of the process that we go through.
I think that's why guessing and checking part was the most difficult part.
Mm-hmm.
Like, why are you like, wait, you can't just rely on only me.
Right. Yeah, that's right.
I need a team of people. Like,
oh, that's exactly it.
Yeah.
No, that is so true, and I think recognizing that's really important too. When you're the reviewer of an article, you know, when you're under, I was just reviewing for the European Journal of Psychological Assessment just before class, right? So I'm a reviewer for this European journal. I guess I'm on their editorial board, and I was sitting there thinking, yeah, this sounds like a bunch of statisticians who just got a data set, right? Because it wasn't very informative about why the items were there, or you know which items they needed to change and why that happened to be that way. It was very much a very narrow focus on it. So yeah, I think it really underscores the emphasis of the changes you make may be good for the data set, but they also need to be good for the bigger picture. Does that fit in the world? Does it fit with a theory? So it's tough. So you think of that as when you're the reviewer and you're thinking, okay, or better yet, take a look at the published articles you've seen. And that's sort of the other thing I like to sort of attack, that you know, peer review is a really messy process. It's not perfect. I'm co-editing a journal, like I'm the one making editorial decisions on articles and whatnot, and I'm acknowledging, you know, we're gonna make mistakes. We are. So I always like to say peer review should really be in the eye of the reader, regardless of whether the paper is published through peer review or not, right? So when you get a published article, it went through some type of vetting process, but that's not the ultimate. And if they didn't get the right people reviewing it, if they didn't get the right, or God, I've seen so many things in peer review where it's been, well, you know, I just called the editor and I convinced them otherwise, or something like that, right? So, absolutely, Shada.
Yeah. I was wondering if you think that eventually in the future, for these kinds of articles, for certain journals,
Mhm.
if you imagine that a person submitting their article would also submit like their code.
Absolutely. And that's sort of a great idea. The push toward open science is big. So I was at I think I mentioned this, I went to this thing for the NSF and AERA held this summer, you know, representing my journal, about trying to get journals to embrace more of an open science part of it. And that's one of it. The code itself is fairly easy to give away. It goes beyond that. There's a lot of people who want to just have you share data. And you know, there's a lot of ethical issues, but not going into that. But I think, yes, anything that where you can replicate an analysis, but then make the result reproducible in a different sample would be important. And code is the first step to just even seeing if the analysis was done right. There are some journals out there, I don't know of any in the fields that we might be in, but I did hear at this thing in DC where they insist, I think it's in political science actually, where they will insist that you not only send your data, but you also send your scripts, and then they have some part of the editorial team replicate your numbers from your scripts, even just to make sure the numbers are accurate, right? And so that's well, you think about, like, there's a couple things that does. I mean, first of all, the burden on the editorial team is going to be really impressively high, but then also, I mean, that does provide some help. You know, it sort of makes it so that the data are a certain way and the script comes in a certain way, so that you can always make it easy to reproduce it, right? So I think that is a good thing. I think we're still in a place where, you know, when I first went into the open data, I thought about it sort of disincentivizes the need to collect data, if that makes sense. And so, like if you're going to spend a lot of time, effort, and energy, even if it's grant supported, collecting data, and then you go and share that with the world, what's the incentive on the collector part to put in that investment if everybody else is going to publish with it too, right? If I could just sit back and let Craig spend his time and effort collecting data, and I take his data and do whatever else. And so I think we're still working through issues on how do we share data well. Then, of course, there's in schools, particularly if you're, I know you come from the special ed group, or if you're working with smaller sets of students, it's really hard to de-identify students or schools or however, because ultimately you start narrowing in the sample. So there's these issues we have to work through. But yeah, the script itself is a good idea in the first place.
Is there a way to like publish like a data set?
Yeah.
Like cited, so here's my data set.
Actually, yes. What they're doing in certain places now, they have these data repositories. So the AERA journals have access to, there's a group of universities called the Inter-University Consortium for Social and Political Research, ICPSR, run out of University of Michigan, but we're a member of it, and a lot of other, a lot of universities are, I wouldn't say most. And so basically, if you publish in an AERA journal, you can house your data there, but they provide a DOI number for your data. And so that means you can talk about how many times you cite, people are citing the data, or, I mean, you can talk about downloads and whatnot, but that's actual citations for it is becoming a thing. So they're trying to make it count where your impact, if you're talking about how many times you've been cited, if you've got a data set that's really well, it's now an incentive for you to make it public, because now, okay, that's going to impact the field as well. So I think but it's still not, people don't think that way a lot. And again, even if you did think that way, certain fields don't lend themselves well to that even. I mean, in my field, in the journal I edited, the society we represent, National Council on Measurement and Education, typically the data sets are children in classrooms. It's educational measurement of some sort, but they usually either are in states or they're from private companies, neither of which want to make it open. For very good reasons in different directions, right? The private company contract with the state usually to get assessments, and so their contract says they can't, and then the state itself has a desire to make sure that the students are, right? So there's sort of a lot of minds have to change in our field to even get to that. So, and that's just one exemplar. There's a lot of other places where it is too. So it's an interesting world. Thankfully we're having the discussion, because I think having a more open science is a good thing. The interesting thing that at the start of the meeting, one of the officers at NSF started by saying, the average sentence length for the New York Times, I think I may be quoting this wrong, but it's roughly 11 words per sentence. The average sentence length in an academic journal article is like 17, right? And it's like, you can't make it so that, people who are, in a very narrow field talking, they understand that field well, speak to a broader audience, but, how do you reconcile, if the public is supporting science, but science has become so nuanced that the public doesn't understand what's going on, you have to have, there's sort of a scientific interest in making sure that our results are translatable beyond that. They also talked about them. They asked the question, what is the modal paper that's been accepted for a journal? How many times is it cited? And I think the answer was 0. And the second highest number was 1. That's right. Yeah.
Do any, sorry, this is another change, but do any of those journals, do they have like in our field, it's like a practitioner section, where basically they might have one article that gives you like all the heavy duty analyses, and then basically something else that says like, this is what it all means. Yeah,
that's another way of doing it. I think you could do that too. Some of the journals do. We don't at my journal, but actually I'm trying to even suggest that too, kind of a novel way of doing practice.
Like knowledge translation.
Some of the quantitative journals, I'm only familiar with the quantitative journals. So it's like the journal Structural Equation Modeling is a fairly highly cited quant journal for the quant journals. Now, it's not a highly cited journal in general, but they have I believe the reason they're highly cited, I don't believe they break down where the citations come from, but it had this long-running section called Teacher's Corner, which is essentially, how do you do this, right? And they have their own editor, special editor for that section, but that's a piece that people from other fields of like, hey, we're going to come into, something called invariance testing come out. Well, go find the invariance piece in Teacher's Corner and figure out how to do that, and then you cite it, and next thing you know, the journal looks better. So Yeah, I think that's a good thing for journals to explore. I think it is an important thing because it does. I do recognize, working in narrow fields, I recognize the need to be narrow, but also there is a need to be broad somewhat too. So anyway, sorry, this is a great conversation. I should probably move on to more things. Just philosophy of science is great. So do you remember, we're going to need to get to IRT though. So I've looked at our schedule and I looked at what we have for IRT, and I made a decision that I'm going to focus our IRT discussion on what Lavon can give us in R. And I say that because there's a lot of IRT out there, but what Lavon is giving us is also what M+ gives by default, is not sort of the gold standard. It's sort of a very good way of estimating things, but it's not maximum likelihood. How's that sound? I would say maximum likelihood is sort of our gold standard, but one of the problems with that in IRT is that they sort of expect you to have huge sample sizes. And looking at most of the data you submitted, that wouldn't fit with it. So this way that Lavon estimates it is actually very much in line with the sample sizes you have here and from the homework 3 that I just read. Long story short, if you'd like to know more about the bigger sections, the maximum likelihood version and so forth, please read the rest of the slides. Take a look at my website. Take a look at the link to Lisa Hoffman's website. There's a whole, I've given entire courses on item response theory with lecture videos. I don't know if the videos are, I think they are. Last time I taught it up at Michigan, I put the videos in my voiceover. So you can go and learn all about that from my website if you'd like, but I think just to focus on class, we need to restrict it to what we can do in Lavon. And here's the sort of the dilemma I faced when putting this together. So M+ is great in some respects because it will do IRT in different ways. You'll have a lot more, it has a lot more options than Lavon does, right? Lavon is sort of M+ light, M+ free. Doesn't give you all the options. People haven't developed it yet. So sometimes you might run into a situation, for instance, in the next set of slides, it's what if you don't have binary data? What if you have like count data? Well, M+ might be able to do it for you, but Lavon can't. Right? So that's one issue. Sort of not all the distributions. So the other issue that we have is that if I were to switch out of Lavon to do it, there's a great IRT package in R called MIRT, M-I-R-T, and it's very good for doing the scaling side of test construction. So basically, you put things together to give a number. It has a couple options for what it calls latent regression that is like structural equation modeling, which is ultimately a simultaneous analysis where you want to predict the latent variables or whatever else. But it's not really well suited for that either. So like the one place I would go for a good IRT package is also not great for SEM. So we're sort of stuck. So we're going to stay with Lavon. We're going to talk about a couple types of data, binary data, and then ordered categories, right? So what if you have a Likert scale? Those are categories. The higher number represents more of an opinion than the lower, but you don't know how much more, something along those lines. So that's where we're going to focus. If you'd like more information, please do see my website or send me an email for everything else. Okay?
Do you not teach that IRT class anymore?
Billy Skorupski teaches it for us, and if I were to go teach it, he'd probably get really, really angry. No, I wouldn't say that.
So you're going to do it.
No, I'm not. No, he's a good instructor. I think other people have had him, right? Some of you have him this semester. He's a good. Yeah, he IRT is sort of in his wheel. That's his research area, that and Bayesian. So I don't think I'll ever teach it here. And this class, what he does well in that class is very much into each of the types of models that are there, but also into sort of the things that come in industry that we need to do. So we sort of see it in science, but it's a little bit less problematic. In industry, one of the things we have to do is something called equating. So like if you want to take this year's tests and make sure it's comparable to last year's test, there's a process you have to go through to do that. And there's all sorts of ways. So he teaches a section on that, for instance, and we're never going to touch that here. We often don't talk about that in science, so sorry. Okay, any other? So let's think here. I talked about logits before. Lavon for get back to where I clicking on my computer. Sorry, I'm an idiot. I'm clicking on my computer for it's not clicking. The menu isn't working yet because it's on your iPad, dummy. So anyway, let's just move here. Sorry. I can call myself stupid, right? I can call myself an idiot. I try to make fun of myself to remind myself that, you know, no matter how long you've been at this, you can be pretty stupid about it. Anyway, we had talked about logits before. Do you remember that? That was a fun conversation, wasn't it? Well, it turns out Levon doesn't use logits. They use probit. So probit. What is a probit? So let's take a look here. If I were to draw, there we goes. So if I were to take the probability an item for a person equals 1, conditional on, now in IRT we typically turn the factor into theta. Right? This was F in CFA, right? So wherever you see theta, this is my way of drawing it, that's factor. That's just sort of an IRT convention. What does this happen to be? Well, again, this is a probability, so again, that same thing applies. We need to worry about, for each level of the trait, transforming the linear CFA model into the bendy IRT version, right? And a probit is given by the following. I'm going to draw an integral here, but you don't have to think about it, right? If we were to take a normal distribution, the normal distribution PDF of 1 over the square root of 2 pi, the sigma squared is 1 here, times e to the theta minus 0 over 2. And we do this with respect to theta, and we integrate it from negative infinity up to what we'll call a threshold here. This represents the probit. What's that? Okay, this thing right here is the normal distribution. Let's pretend underlying a variable y, underlying this categorical variable, we have some type of continuum y star. The normal distribution talks about, this is, by the way, a tau. That's supposed to be a tau, a threshold for the item. If that threshold was, let's say, at a value of 1 here, then this integral represents the area under the curve right here. And so what ends up happening, and actually this shouldn't be theta. I've just completely screwed this thing up. This thing right here shouldn't be theta. It should be your typical IRT model, or in this case, negative tau sub I plus what we're going to call lambda theta. So this lambda represents our factor loading. So this is our y star. Well, this is a crazy looking integral. What I'm talking about here is ultimately we take this continuum over here. This is the thing that we would get from our linear predictor. Like if remember in CFA, we said y for an item in person was equal to mu plus lambda times f. And then we had error. But this part right here was our predicted value. That thing, that predicted value, ranged from negative infinity to positive infinity, right? That's all the values it could be. If we took this predicted value and put it into that integral above us, where if we took mu, and this thing right here was negative mu right there, we call that negative mu. If we look for the area under the curve, we now take whatever predicted value this is, and we talk about how likely it is to occur under this distribution. Well, I'm really screwing this up. So let me go back. So what we get here is this, and I'm sorry about this. I'm talking about this. This is our latent response, effectively, for binary data. So what goes on in a probit is the following. It basically says the probability of y equals 1, or this probit function, is given by the inverse. Now this is your model. This right here is effectively mu plus lambda f, right, in factor analysis. That's sort of where it goes, and it goes into this function which puts it onto a probability. So ultimately, that's the big picture, right? You're not just looking at the predicted values straight on the number that would come from it. You have to go put it back into a probability to make it work. What does that probability mean? So one quick thought, probit versus logit, should you care? Not really, they're both about the same. Whether you use probits or use logits, you're going to tell the same story. The difference is this: if you wanted to turn a probit into a logit, you multiply it by multiply everything by 1.7. Almost. It's almost the same thing. If you wanted to turn a logit into a probit, you divide it by 1.7. 6 of one, half of the other. The problem is, so what happens is so you've got these people out there in the world. I shouldn't be talking about this now. I should really go through what we're doing first and then go back to this. But the idea is this: there's sort of a decision you have to make. I'm going to use M+ and use logits, or I'm going to use MERT and use logits, or I'm going to use Lavon and use probits. And you're like, oh, probit versus logit, is that an issue? Not really. That's what we're trying to say. They're effectively the same thing. They give you a bendy line in probability, and actually this is the line. I don't know if you can see this. There is a bunch of dashed lines there, and that's the probit, and the dark line there, that's the logistic, and they're effectively the same, right? So there. So get back to our measurement class. I think we talked about this. IRT, what we're doing is effectively called item factor analysis, but it's a form of IRT. This is the probit version of it, sort of. It's called item factor analysis. Again, items and people matter. It's the same type of thing. But now, after controlling for a person's latent trait score called theta, which we use to denote here by the Greek character theta, items should be uncorrelated. Again, that's the same idea that we had over in factor analysis. After controlling for the factor, we allowed the residual correlations to be 0. We said they should be uncorrelated. Right? So that's the first step. And if we didn't, if we estimated a residual correlation, I said you have to call it theta and stuff, right, or factor and stuff. So that's sort of the same thing that applies. In fact, here's the nice thing. Almost everything you learned from the previous section about CFA is going to carry forward into what we're doing in probits. Right? The only difference is going to be how you get the shape of the bendy line. Pretty much. There's a couple other differences, but it's going to seem the same because the output will look very similar. And again, similarly, just like you saw in your homework 3, if the model doesn't fit, we can do a multidimensional model. Sometimes we can worry about testlets or methods factors or other things as well. But where things differ from CFA is that we're using effectively logistic regression or probit regression instead of linear regression. That's it. It's a nonlinear relationship between the factor and the probability of an item response.
We're using logistic regression when we have only binary data. But if we have count data, I don't know.
Well, if we have count data and so forth, it would be like Poisson regression or something for some type of count distribution. Multinomial. The terms start to die off after logistic, but it's effectively the same idea. So here, this is where I want to talk about. What are we going to get when we talk about item factor analysis? What do we get out of Lavon? We're going to get a model that has loadings, factor loadings before, just like we saw in CFA. But instead of the mean for each item, now we're going to have something called a threshold. A threshold, we're going to describe a little bit more, but it's effectively the point in the underlying continuum where you switch from going from a 0 response to a 1 response. Right? And if you have a model form with loadings and thresholds, and you estimate it with something other than maximum likelihood, something we're calling limited information, that's where the label item factor analysis gets applied. This sort of grew out of the 1960s and 70s when Lizroll became big, when maximum likelihood CFA came along. What people started doing, Christofferson, Bank-Mutane, who developed M+, started saying, well, if Lizroll works effectively on covariance matrix, if I could just plug in a covariance matrix and make it work, which is what we could do with Lavon too. I said, don't do it, but we could do that. Well, what if I swap out that covariance matrix of the data for something that's a correlation matrix of my categorical variables? Because ultimately, I don't, in data, like if the machine is going to do IRT or CFA, I've got a method that says, okay, give me your covariance matrix, and I can predict what that needs to be. But what if I just, instead of putting in our covariance matrix with our plausibly continuous normal data, What if I swap that with another form of covariance matrix for categorical data? Would that work? And sure enough, it does. It's effectively how they started doing this. So it started with this idea of limited information. It starts with the covariance matrix, not the data itself. That's in contrast to IRT, which also started right around the same time. It became really big in the same time. Item response theory, there was a PhD dissertation that turned into a monograph by Frederick Lord in 1950 that did the same model that we're going to do, the two-parameter normal ogive, but tried to do it with maximum likelihood, or talked about it with maximum likelihood. And then in 1960, Roche came out with his model. And then in the late 60s, Frederick Lord, wrote a book with Novick, 1968, that described all about IRT. But the main difference was the way they parameterized it was slightly different. They called it discrimination and difficulty. So it didn't quite look like our nice regression model that CFA looks like, which is what IFA looks like. But they also did things with the logit distribution, the logit link function. And logit was used in the late 60s because it was a lot easier to implement on a computer at that time than probit was. Probit involves this weird integral and there's approximation to it that takes a little bit more time. Logit's just a straight function you plug in and you get an answer. So why we're doing IFA is because that's what's available. Well, again, you can call it, they're sort of, the names are synonymous now. Yeah.
I guess that's part of my question. Why would somebody choose to do something with limited information than full information?
Well, full information is, the main answer to that is missing, not missing, small samples. Where limited information seems to outperform full information based on several papers former colleague of mine, Debbie Bandelos, published maybe 10 years ago or a little bit shorter than that, showed that, you know, full information maximum likelihood, if you don't have a big sample, then sort of what you get starts to fall apart at some point. Whereas limited information seems to be a little bit more stable for the smaller samples.
And then what would you say is like small versus like, so what would be the cutoff?
Okay, so to do the typical, if we took our translation of CFA and put it straight into IRT, that's called a two-parameter model. So each item would get some type of threshold, which would be the analog to the mean, and then some type of factor loading. People in the IRT world, if you go take Billy's class, and I don't want to paraphrase Billy, but most of the time they'd say sample size in the thousands. How many of you have sample size in the thousands? I mean,
Yeah,
Jesse,
Jihong.
Jihong.
I have 4,000.
Oh yeah, 4,000. Well, that's good. So, but
Enough.
yeah, there you go. So ultimately, full information seems to be talked about as a large sample size technique. Now, there's another version of estimation that's not shown on here that, again, we're going to sort of be updating in the next few years, which is Bayesian version. And I would probably think Bayesian is superior to both, but that's a topic for another day. And again, I think next fall, I want to teach this class, but do it from all Bayes, like as a special topics or whatever else. So, but I think that helps a lot for small data, but it also helps in large data too. So anyway. Yeah, Jihong.
So can we say the limited information just use the model for variance?
That's right.
And ignore the model for mean?
Not actually, no, that's not quite right, because what ends up happening is the model for the mean and the variance in a categorical data is combined.
Oh, yes.
Right? So because a Bernoulli variable only has one parameter, and it is the mean, and the variance of Bernoulli is the parameter times, or the mean times 1 minus the mean. But what you can say is limited information uses a summary of the data rather than the actual data, whereas full information uses the item responses directly. Limited information takes the item responses, converts them into some type of correlation matrix, and then uses that to do the estimation.
What does NB stand for? WS?
Yeah, that whole thing is a mess, and actually it's going to get worse in Levant. It stands for weighted least squares mean and variance transformation. So the method for estimating that we're going to use is very much like what you used in your regression class, least squares. We're going to sort of take a difference between something predicted and observed. Well, the thing predicted is going to be a correlation, and the thing observed is going to be a correlation. And so it takes the square difference and it weights it by something. But then to figure out the weight and to figure out sort of what to do with a hypothesis test, it uses a transformation that I don't fully understand, to be honest with you. I don't think I've read it, but it's just something called from Albert Satora and Peter Bentler that talked about how to transform it so it's more appropriate for data in most cases. It's a little bit more robust.
When you say weight, is it a constant?
The weight is not a constant. It depends on features of the data itself as well, which is also, we're talking about like features that are like fourth level moments or things like that, but it's a little bit complicated. Bendy. Sorry.
Okay, the mean and variance.
So what again, it's going to basically take a chi-square and rescale it based on other properties of the data. It's very similar to that robust chi-square that we saw in CFA. It's a rescaled version of it.
So is it assuming that all the items would be in the same scales?
No, it's assuming that no, not at all. So some items can be binary, some items can be polytomous, like ordered categories. Some items can even be continuous. It just assumes that you have the covariance between the items accurately represented. So it's an interesting. Again, here I'm hitting my computer. It's an interesting world to live in. But we'll try to walk through it. Let me try to give you some more information. What we're used to, this is the Logit version of it, but we're used to this type of linear model, and we're going to transform it into, basically the idea is our linear model, it's not going to have error, right? Normally we'd had error in CFA. We're not going to have that part of the model, so we're not going to have residual variances. But then we're going to do some type of transformation to convert it into a probability. This is the inverse Logit probability right there. But then for us, we're going to end up with a probit itself. One of the things, so actually we'll talk a little bit about this because the form of the model starts to be the same. The simplest IRT model that you can come up with is something called a one-parameter logistic model. This is the Roche model. Equivalent to the Roche model. It depends on a few other nuances that I don't really care to get into, but effectively it's this. If you were to talk about the probability an item response is equal to 1, again, this function, whenever you see e to something over 1 plus e to something, what you should be translating in your head is, that's Logit, and actually that's an inverse Logit. We're going to do some other type of phi function with it, which is a probit. And that's that crazy, basically what's in here is a z-score. We're going to go figure out the probability of the area under the curve that goes up to that z-score, right? So that's, but what's inside the parentheses is the part that matters. And so this part that matters right here is you have the theta for a person and you're subtracting for an item what's called the item difficulty. So in this case, what Roche model is doing is it's providing a scale for the subjectability. Again, you have to fix its mean, fix its variance, same type of thing that happens. Often in this one parameter model, because if you look at it, there's no factor loading multiplying the factor itself. Here, if I can go back over, let's take the core of this one parameter model. The core of it is the, in this case, this is the probit of the probability that y for an item and person equals 1 given theta is equal to theta for the person minus b for the item. This is the core right here. So let's map that onto what we know. What do we know? We knew CFA looked like this. It looked like y for the item and person equals mu plus lambda for the item times f for the person plus error for the item. And that was our CFA model for one factor. So let's go and take this core and convert it into what we're talking about. So the y, our y now is now a probit, so effectively, right? And what that does is it makes us drop off e. This is gone. This is due to categorical data. Right? So effectively, we don't have e. Where is error represented, though? error is represented in this result when it gets transformed back into a probability. It's the distance from 1 or 0. If that probability for everybody is like 0.6, there's a lot of error there, right? Somewhere between 0.4 and 0.6. But if it's a model where half the people have zeros and half the people have 1 for probabilities, there's no error whatsoever. It's a straight... So that's where error gets re-represented, if you want to think of a place for it. What else? Let's take theta minus b. If we take theta minus b and just reconverted things, if we turn this into b sub I plus theta for the person, now we're starting to get things that look a little bit similar, right? Here, there's nothing multiplying the factor. Factor and theta, first of all, these are the latent trait. Right here. And you see right here in the CFA model, there's a factor loading. In the Roche model, or in the 1PL model, one parameter logistic, this is not there. It's the number 1 times. So basically what we've done is set all of our factor loadings equal to 1. Does that remind you of any model? Almost. The parallel items model set all the factor loadings to be equal. And sure enough, when we set all the factor loadings to be equal, but we fix the factor variance, right, to 1, that's equivalent to setting all the factor loadings to 1 and estimating the factor variance. So it's like a parallel items model. The only difference is what are we doing with the factor, what the number happens to be. So effectively, we've set the factor loadings to 0 to 1, or set equal factor loadings. Right? The other part, right here. Our mean for an item is now represented by negative b. Right? And so ultimately, what we end up getting here is that this b term is not an intercept, but we actually has a name. It's called item difficulty. So item difficulty is the level at which it has an actual definition. Right? Think of it this way. If we had a scale here, if we had with one side over here theta and the other side over here difficulty, right? If you had a theta, let's say it was a 1, and you had an item difficulty that was 1, what would happen to this? We would have a 1 minus a 1, which equals a 0. Well, the integral on the normal distribution from the standard normal from a negative infinity to 0 is 0.5, right? So 0, whenever you have theta equal to b, represents the 50-50 point, the part to which a person has a 50-50 chance of answering the item correctly. Right? So this is 50% chance, or yeah, 50% chance. I could talk about the nuance of that 50% 0.5 probability of y equals 1. Right? So item difficulty is the spot where there's a 50-50 shot a person has the right answer, has a theta of that value has a...
The value on whatever the distribution is that we're modeling, that value is our b here, and that's the point at which they have 50-50 chance.
That's right. That's right. Yeah, so the item difficulty itself, yes.
So it's moving like it's affected by the theta ability of that individual.
That's exactly it. So b and theta are on the same continuum. Right? They're on the same metric. So basically, we're taking items and putting them on the same scale as people. Well, it turns out in factor analysis, we were actually doing that too up here. We just didn't have a translation that gave us an anchor point of 50-50. Right? Yeah, Shada.
So thinking about if they have this 50-50 chance of y equals 1, if your anchors are like agree, disagree, not right and wrong, then that would mean you have 50-50 chance of either agreeing
or being indifferent. Yeah, I guess.
You're just indifferent.
That's right.
Interpretation difference.
That's right. Yeah, so it really and again the IRT world came out of educational testing. So right or wrong is where item difficulty got its name, right? So if you remember in classical test theory, item difficulty was the proportion of people who answered the item with a 1 or correctly, even if you had agree, disagree.
Yeah.
The higher that proportion, the easier the item happened to be. In IRT or IFA, the item difficulties go in the right direction. The bigger the B value, the more you have to have of the trait to have a 50-50 chance of answering it correctly. So it's in an educational sense, it's a harder item. In an agreement sense, this is an item that very few people will agree to.
So, for example, if we have very difficult item, like for example, at the theta 3, which is like far away from the average, from the midpoint. For those, the 50-50 chance would be like would represent a small number of response.
That's right. So what you're going to have, often if you think of theta having a normal distribution, doesn't have to. I mean, sorry, having a standard normal, right? So if theta is normal, the mean of 0, standard deviation of 1, then a value of theta at 3, like right here, the proportion of people beyond 3 is less than 1%, right? So having someone at 3, if you find an item difficulty at 3, that's saying that less than 1% of the people have more than a 50% chance of answering that right item correctly.
So that's how whoever makes the assessment manipulates.
Part of it, yeah. Yeah, if you it's part of the equation. We're going to see a little bit more. There's another factor that complicates it once we move past the 1 PL.
Can you repeat that? You said the bigger the B value, then the more...
The fewer people are going to have answer that correctly, because ultimately...
The bigger the theta or the B?
The bigger the B value.
Oh, the
bigger
difficulty.
that's right. The bigger the
Yeah.
difficulty.
Yeah.
And again, if you put it, difficulty is that charged educational measurement word. Think of a math test. The bigger the B, the harder the item, the more difficult it is. That means fewer people are going to answer it correctly.
Which is the difficulty or the B value would lie on the theta, is like corresponding to that.
That's right. That's right. So again, this is like an intercept, but because our scale, our whole world is no longer in just units of the variables, right? In CFA, it was Likert units, if you had a Likert scale, right? It was, mu was on that scale. But because we're in probits now, the mean probit is like 0, right? Or logits also, mean logit 0, right? And so this provides an actual meaning of 50-50 chance of answering one way or the other. So, here's some fundamentals of where this goes. Back in classical test theory, scores only had meaning relative to people in a sample. So for instance, if you got a 12, you wouldn't know if that's good until you figured out where you were a percentile rank in the class or in the set that you had. In IRT, we're actually doing something called conjoint scaling. We're taking items and taking people and putting them on the same metric. And now this is the odd thing. Everything I'm saying about IRT still applies to CFA. Right? We just never talked about it there because the metric of Likert units wasn't as important. In IRT, this is sort of what the people who developed the method sold this to replace classical test theory for educational purposes, for the most part. But here, what we can do is construct a construct map. Now, this is Lisa's construct map because I know nothing about 80s pop culture, and I tell her, you need to turn the page. But no, I'm just kidding. Anybody like the 80s? No? Good. Well, let's see how bad it would be. Like, so if you had over here the item side, this is a person's theta, and over here you had, sorry, the person side, this is theta, and the item side, that's B. We could talk about how hard these things happen to be, right? If you went to Lisa's mom, she might recognize who the singer of the song Mickey was. Thanks for making me sing it. Yeah. Do you know who sings it then?
No, I can't think of it.
Does anyone know this answer?
There are a lot of covers of it. I think I have a cover from the Trilogy movie Bring It On.
Ah, yes, good movie. Unfortunately, I don't know what that happens. So I have zero. Here's the interesting thing with me. I have very little knowledge of the 80s because evidently I was growing up then. Or either that or I was just high the whole decade. And I don't know. The Cosby Kids. If you can name the Cosby Kids, Lisa thinks that's the average adult. Now, we're all adults in here. How many of you can name the Cosby kids?
Sorry.
Rudy.
Ruthie.
Yeah. I was gonna
Rudy
say-
or Ruthie? I thought it was Ruthie.
Rudy, I
I
thought.
think Rudy. Oh gosh.
Hey Siri,
I knew that.
who are the Cosby kids?
My web search turned something up for who are the Cosby kids.
You know, let's just leave Cosby in the past. It has a new connotation altogether now.
Yeah, it's
It's a little bit weird.
The Donger, anybody? That's a movie.
born at the end of the 80s.
Yeah, no, so this is an who is it? John Hughes? 16 Candles, maybe something like that.
Oh, the guy that was in the tree.
Yes, that
Yeah,
one.
yeah,
Yeah,
yeah.
yeah. Okay, so there. So maybe undergraduates know that. See, again, this is not an pro. She created this slide maybe 10 years ago, and that was much more. We had relevant class now. Wham! George Michael was the lead singer. Don't know anything they sang, but I did know this. This one I know. The Home of Alf. Does anyone know what Alf was? The TV show. Yeah, it was an alien life form. I believe it was Melmac. So anyway, point being, you can sort of describe people by what they could answer. And that means my theta for the 80s has to be high, right? Either that or that's not a unidimensional continuum. Anyway, point being, you can put theta and items on the same metric because of where that happens to lie. It's harder in CFA because each item doesn't have a common, because you're on that Likert scale, the mean itself is a bit different from 0. So you don't have a point where it's 50-50 chance or where it's right in the middle of the scale. If you mean-centered your items, though, if you subtracted the mean off from every item, then the intercept in IRT would be 0, and then you could describe sort of how each item would happen to look, or each person would happen to look based on their item. Shada, do you have a question?
So a person with your 80s pop culture knowledge, you would expect them a person with your theta, you would expect them to know
All the rest.
what Home of Alf is.
Yeah, that's right. You would expect me, or at least have a 50-50 chance of Home of Alf. But the other thing is, because this is a harder item, I should have a much higher chance of knowing these
Gotcha.
other things as well. And clearly this example breaks down here.
Okay, so Home of Alf is hard.
That's right.
And Mickey's easy.
Supposedly. But to us, we see we're not in the right population here. I pretty much hate the 80s. Like, I guess, you know what? If you asked me about late 1980s baseball, I could tell you that, right? That's probably what I was into most in the late 80s. In the early 80s, I don't know what I was into. Maybe eating, breathing.
So
Mickey
based on
Mouse.
this, you're the most not knowledgeable. Like
It should be.
the most chance of getting these right, and then your mom would be the least likely.
That's right, yeah. But the thing is, so if you think about this, why this example breaks down, I could answer that hard question right, but none of the easy ones.
Yeah.
And if you see a scale like that, it's not going to fit the data well, right? It's sort of an easy analogy we can make. Here's another one. This is a norm reference measurement. These are 4 people. This is from a book where you have 4 different people and their scores based on where they are in the sample. But if we did this in IRT, we took this is an item difficulty of adults, I believe, executive functioning in older adults. So this is basically, if you estimate each person's theta up here, and you compare that with the activities that represent the items down here. Theta being at the level of the item means a person has a 50-50 chance of being able to do each of these activities on their own, from what this scale means, right? So Anna has a hard time, has a 50-50 chance of grooming herself, but has less than 50% chance for the items that are harder. Whereas Vera can even transfer from a tub to a wheelchair or out of the tub to in the tub. Has a harder time with stairs, but has much higher chance of doing the rest of those items themselves. So what this is doing, what I'm trying to say is that in this framework, the metric of the parameters provides 2 things really good. It provides you an understanding of where people happen to lie on where you're at without having to know about the sample. You can see them relative to the items themselves. But it also provides a sense of how to understand what a score means, like a validity purpose, essentially, right? A person with this type of score has a 50% chance of being able to go to the toilet on their own, as an older adult. Again, not a great...
So when you mentioned validity
Mhm.
in this context, you mentioned before like assumptional validity.
That's right.
How you Can you?
Same thing here. Assumptional validity before was whether or not the model fit the data. And so in this example, the assumptional validity was off because the model didn't fit the data. If there was a person in this room who could answer these questions, you hid yourself very well. And the one person that answered ALF was me, but I couldn't get the other ones right.
What I thought about is, can we talk about not assumption, but score validity for each individual? Like, if we, like, for example, if we observe that some of the individuals in this, like, test or whatever, their score, is some of them similar to the examples that you gave us about the ETs, but some others are a little bit different, while still others show the consistency from answering difficult questions, all
so like a person fit measure.
Yeah.
Yeah, there are versions of that. Let's not get hung up on that right now. Think of it this way. If it doesn't fit one person, it's probably not going to fit a lot of other people. And if it doesn't fit a lot of people, the whole model doesn't fit, right? So I think hold off on that thought for right now, though.
I just have a quick question on the next slide after this one. So
this one.
the one before that.
Oh, this one.
Yeah. So y-axis then would be their score.
It'd be like their z-score.
Their z-score.
Yeah, if this was a classical test theory test, if all you had was their score and you sort of standardized that, you couldn't tell what each of these people could do. You could just tell they're higher or lower, whereas what you're trying to do is put them on the scale of the items. Hold on to that question about person fit, or maybe talk about it after class, because it's going to take us on a route I don't want to go right now. So there's some people who talk about theta being sample-free or scale-free or whatever else, and we still need a sample to calibrate our items, so I'm not a big fan of those words. What that really means is, in reference to classical test theory, the theta estimates are disentangled from the rest of the norming sample, right? You sort of have, thetas, each person's thetas, each person's items, but if you change the test items, if you swapped out one item in classical test theory, it throws off a whole lot. But IRT doesn't necessarily do that, because ultimately the item comes in with its own difficulty, and if its sample of people have the same properties of the sample of people you have, then you put that in, and it just helps tell you a little bit more about where the person lies in your sample. Whereas in classical test theory, to figure out where a person is, you have to know all of the people, right? So what we're trying to do is disentangle. It comes from the idea that each of the items are getting modeled separately, is what this is really talking about. When we do each of the items separately and we do each of the people separately, we get this approach. It still applies in CFA, believe it or not. So the other thing that happens in CFA that doesn't happen in IRT. In CFA, there's one number of reliability for the entire test. So each score uses, my reliability is this, omega, alpha, whatever you want to call it. In IRT, that is not true. Reliability is often talked about not as reliability, but each theta is having what we call a conditional standard error of measurement. Right? So they're related. The smaller the standard error of measurement, the bigger reliability. Right? So they're inversely related. What happens in CFA in IRT is because of this non-continuous, because we don't have normal data, the mean and the variance are tied together, and so it sort of affects what our standard errors happen to be. So not everybody has the same reliability is what I'm getting at.
So the bigger the standard error of measurement, then
the lower the reliability. That's right. The way I like to think about it is if you were to draw like normal distributions around these people. Now again, it may not even be a normal distribution, which is the other weird thing, but each of them has sort of a width. That's our standard error of measurement, right? And so it might be very big at the top, it might be more narrow right here in the middle, and it might be really big down here. The more narrow that you have, that represents higher reliability. So, right? So if you had no interval whatsoever, then effectively that score is exactly right. And if you took another test or whatever definition of reliability you want to use, you'd have perfect correlation of the score here and the score from another instrument, or half of the other items, or whatever else.
So it's reliability of the item.
It's reliability. It's still reliability for the factor.
Okay.
So, going back to what you have mentioned before, like about the GRE,
Mm-hmm.
when you mentioned that they didn't provide like
Standard error.
standard error for.
That's right. That means each of your GRE tests might have a different reliability.
Which is which means that the equating process is not, because if we are,
It's not about equating. It's just because of the way that the properties, the items that you took, because you took a different set of items, they might have you. It might lead you to. It actually may be the case where two people have the same score and have different reliabilities. Depends on which items that you took.
But still, if I took on items that is completely or different from yours, we are testing differently the validity of our.
You would think the validity suffers, but that's another topic. If you believe in the reports, validity is another topic, right? So, but if you have these items jointly, another thing about IRT is that you can concurrently calibrate it. So even though you don't take the same items I take, they're on the same metric. You can make sure they're on the same scale. Validity means is the label I attach to it really an accurate label, and we can't tell that, but we can say they are on the same metric by equating. So what we end up getting is scores that are comparable. The thing that we can debate is whether or not when GRE says it's mathematical ability, if it really represents mathematical ability. That's validity, if that makes sense. So, but ultimately, what this means for you, for practically speaking, is another part of IRT that doesn't show up right here that really we talk about is that our scores that you get are almost always factor scores. Right? There is no option most of the time to report sum scores. And excuse me, you could see me fighting it. It just broke down. It broke through. The sum scores, there are occasionally you'll see, particularly this happens in state assessments, where if you took a grade report from someone who took a end of grade test, it might look like it's on the scale of the number of items of tests, but often that's a linking that's done from that scale score to the factor score itself. So they translate kind of where the factor scores are and what the average level of score, observed scores for. So again, it starts with the factor score. So this is the other odd thing about it. That's why I teach CFA the way I do, is that most of where we see our scores from tests come from factor scores. You know, if you think about large-scale testing, you think about the tests you've taken as a person, you've probably been given factor scores more than a sum score. Yet if you only learn CFA or classical test theory, that's all you'd calculate. So we sort of need to cross-pollinate the two. There we go, I'm touching my screen again. So there's another version of this 1PL model that shows up, and that's where we have a common, what's called a discrimination parameter here. So what does this look like? So if I go back to my notes, the model that I had shown you before was theta minus b, right? I'm just going to put p over here for probit, person minus item, right? And often when this model gets estimated, theta follows a normal distribution with a zero mean, and we actually estimate its factor variance. Because from CFA, we can do that because effectively we've made the constraint to the factor loading, right? We could estimate that just fine. Another variant of this is to do the following. We have something called A for an item, where we take theta minus b. But now theta often follows a normal distribution with a 1 for a variance. And these two models are equivalent, equals. In fact, what you can show is that A squared is equal to sigma squared, if I'm not mistaken. All right, you can actually show that the two are tied together. But let's disentangle this model real quick for a second. And actually, I screwed up on how I wrote this. This is, there's not an index for I here. This A is the same value for all the items. Now, this is our tau equivalent model. So hang on just a second. if I were to rewrite this for a second, we get negative A times BI plus A times theta P. Yes, Shada.
So I understand why you need to multiply A times B because you're accounting for the discrimination amongst the items as they relate to the latent trait factor. But why would you multiply that times theta?
Well,
the ability?
Well, here's where it comes from. If you go disentangle this representation, A is effectively a factor loading, right?
Yeah.
So a factor loading. Why did we want a factor loading there? Well, we wanted to allow. Well, in this case, every item has the same factor loading, but we wanted the number in front of theta that talked about how discriminating the item happened to be or how much information the factor is, and that's where that's going from. Why it shows up in this form is because it still preserves the ability for us to call difficulty, B, the same meaning. It retains the same meaning, and that's because when theta equals B, the term in the parentheses becomes 0. And so anything times 0 is 0, so it makes the probability still 50-50. So we put it outside of the parentheses to allow this to still be difficulty itself. But A does not get called factor loading, it's called discrimination, which is not a great term for it. But what are we talking about? Why is A discrimination? Well, let's do a little plot here. If we take the probability y equals 1 given theta, over here on the y-axis, on the x-axis we have theta, we'll color up things here. If I take A equal to 1, my discrimination might look like this right here. This is my line might look like this, right? If I take A equal to 5 here, now my line looks like this. And if I take A equals 0 here, my line looks like that. So what are we talking about? What is discrimination? What is it referring to discriminating about? It's exactly right. It's how quickly you get from the high probability to the low probability in your range of theta. Right? So a high discriminating item quickly separates the high probability from the low probability across the range of theta. A low discriminating item does not.
Say that one more time.
Mm-hmm. The high discriminating item effectively separates people into probability 0, probability 1 with over a smaller range of theta. Whereas a low discriminating item, like look at the red item here, to get to a probability 1 from a probability 0, it's a much wider range of theta where that takes place. Now, one last thing, because it's 1:15, what discrimination technically means is this A parameter is technically the slope of the line that's tangent to the curve at the item difficulty. But that's minutia you don't need to know. If you remember what factor loading means and you understand separating people on high and low probability, you're fine.
So can you repeat that again?
The technical definition?
Yes.
The technical definition of discrimination is the slope of a line that's tangent to your curve at item difficulty for this model. It actually changes for more complicated models. That's why I don't want you to dwell on it too much. But it's effectively part of the way that this is parameterized leads to this description. So if you want to talk about a factor loading is a slope, but that's a slope for all of theta. The item discrimination is a slope, but it's only the slope at item difficulty, or right thereabout. Does that make sense? Okay, now I'm out of time, but I'm going to stop here. If you have questions about this or other things like homework, come talk to me afterwards. Thanks, everybody.